This question is about compound Z with the molecular formula C7H12O3. So if we just look through, we've got quite a lot going on. We've got an infrared, a carbon NMR, some proton NMR, and at the very end, we're being asked to deduce the structure of Z. So I'm just going to go back and remember C7H12O3. Let's just write, that's a top tip, let's just write that down. C7H12O3. So at the end, if our structure isn't C7H12O3, we need to go back and check it. Let's go back and see what we're being asked to do. So the first thing we're asked to do is identify the bond that causes the absorption at 1725. So getting rid of this, what's this? So you need to use your data sheet. This is infrared. So if we go to the data sheet and we look at infrared, here's a value that's containing 1725. So it's a C double bond O bond. Causes the absorption. So that's telling us that one of the oxygens in our structure at least is due to a C double bond O. Figure 8 shows the carbon 13 NMR spectrum of Z. How many different carbon environments are there? So let's tick off the peaks as we count them. 1, 2, 3, 4, 5, 6, 7. 7. Now remembering that there are only 7 carbons in this structure, that means this structure is asymmetrical. It's got no symmetry. No two carbons are the same. State the type of carbon environment that causes the peak at delta 174 parts per million. So again, we need to go back to our data sheet. This time we're looking at carbon NMR, and we're looking at a value of 174. 174 says acids or esters. C double bond O in acids or esters. So let's go back. RC double bond O in acids or esters. Now I'm not going to put in acids. The exam board would ignore it if you did. The reason I'm not putting in acids is because that infrared that we had is not an infrared of a carboxylic acid. If there was a carboxylic acid here, it would have a big peak here due to the OH group in the carboxylic acid. So it's an ester with 7 types of carbon. Table 2 shows data from the proton spectrum for compound Z. Explain what can be deduced from the splitting patterns, so this splitting pattern and the chemical shift value. So at delta 4.1, we want to go to the data sheet and find out what the chemical shift says. So I'm just going to have to scroll back, so my data sheet's here. 4.1. So 4.1, we can see it's this type here. So I'm going to copy that down, RC double bond O, O, C with a H. So that is our type from the data sheet. Oops, I forgot my oxygen, apologies. And the fact that it's splitting is a quartet, okay, so quartet means that the neighbouring C has 3 H's. Now if we look at the integration, we can also tell that this carbon has 2 H's, so we know that it's a CH2 next to a CH3. The peak at 1.26 is a triplet. Triplet equals 2 H's on neighbouring C, because we're using the n+1 rule but going backwards. And 1.26 is just the type, if we look on the data sheet, the type of RCH3. And by the fact that it's a integration ratio of 3, those 3 are these 3. So combined together, we're putting all that together, we've got a double bond O, O, CH2, CH3. We've got an ethyl group. This triplet quartet is an ethyl group attached to our ester oxygen. Deduce the part of the structure of Z that's caused by the peak at 2.19. So again, I've got to scroll all the way back to my data sheet. 2.19 is RC double bond O CH. And we can see that it's a singlet of integration 3. So it's a singlet, no neighbours, type RC double bond O CH, but it's integration 3, so there's 3 of them. So it's telling us all that together tells us that this is a CH3 next to a C double bond O. Figure 9 shows the NMR spectrum, suggests why it would have been difficult to determine the structure of Z using it without the information in the table. Well, it's this bit here. If we go back to the table, we can see that in the table it told us that that was a triplet and a triplet at 2.6 and 2.56. It would have been difficult for us to know that that was that because that does not look like 2 triplets. So we cannot deduce the splitting pattern of the peaks around 2.5 to 3 parts per million. Now we have to try to put all of our information together. So it is a little bit tricky because it didn't ask us to do all the deductions. We know that we've got a CH3 next to a C double bond O. So it's asked us to do this peak and this peak. And we know that we've pulled those together to say there's a CH3 next to a CH2 that's attached to the O of an ester. That was that little section. It's asked us to do this peak at 2.19, and that is a CH3 that's next to a C double bond O. But it didn't actually ask us to interpret these two, which are both things that are next to a C double bond O, and the fact that they're triplet tells us that they're 2 CH2s next to a C double bond O. And actually, if we have all those pieces, it helps us to put our structure together, because then we can count and see we've got 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 carbons in the bits it told us to do. These C double bond O's are the same C double bond O's. So the new C double bond O's in our middle section are the same as the 2 we already had. And then we've got our 6th and 7th carbons here. So I'm going to try to stick all that together. So remembering, I'm just going to go underneath, remembering the little chunks. The exam question led us down a pathway to identify this section. It led us down a pathway at 2.19 to identify this section. What it forgot to ask us to do was the 2 in the middle with the tricky splitting on the spectrum. That was a CH2 that was connected to a C double bond O that was connected to a C double bond O. Triplet, because there's 2 CH2s next to each other. Next to a C double bond O because they were at 2 point something, 2.1, 2.2. These C double bond O's are the same as each other, and these C double bond O's are the same as each other. So our structure, CH3, CH2, and then an O and a C double bond O, connected to the triplet section, connected to the little part that we deduced at 2.19.